Hi, Professor Bob Young back at you. In this instructional video, we're going to look at something not just used in mathematics courses, but your science instructors may want you to know as well, and that is the topics of direct variation, inverse variation, and then a combination of the above two, combined and joint variation. All right, now if we compare two things, like let's just take two variables, x and y, they vary directly as shown here. Here's a basic example. We can say y, if it's directly related to x, would equal k times x. Now, k is some constant of proportionality number or constant that relates the two letters x and y. Inverse variation, and you'll see this when you read the problems, it'll state some type of direct or inverse variation. Y is inversely related to x in this manner. Y equals k over x. All right, so again, the constant of proportionality will relate x and y in a certain way. And then you might have a combination one that looks something like this. And remember, x and y don't have to always be the variables involved. K will always be in there. You might have something like this. Y equals kx over z, where you have both direct and inverse variation. So this one would state y varies directly as x and inversely as z. That's how it would be read. Or you might have something like this. C equals k p z squared over, now I'm really starting to scare people, b cubed. And this would say, if you read this, c varies directly as p and the square of z and inversely as the cube of b. Now, I know some of this scares you here, but these are what we're doing here. What I'm trying to basically set up is just some intuitive modeling here. So let's get to it here, and this might make a little more sense as we go on. So let's start with direct variation, and you've seen some of this in real life. Here's an example. When one quantity is a constant multiple of another quantity, the two quantities are said to vary directly. For example, if you work for an hourly wage of $6, then pay equals 6 times the hours worked. Doubling the hours doubles the pay. Tripling the hours triples the pay, and so on. And this is stated more precisely, as I have kind of led on earlier, in this model. If y varies directly as x, or y is directly proportional to x, there exists a non-zero real number k, such that the constant of variation such that y equals kx, and of course the $6 was our k in that real life example. Now, whenever you solve variation problems, I want you to use these 4 steps. Always, step 1, write a mathematical model involving k, using, if it says directly, inversely, so forth and so on. Step 2, use the given information to get k, and they'll give you enough to set up this model. Step 3, substitute k back into the model from step 1, and you'll get a new formula involving that constant number. And then step 4, substitute remaining values and solve the problem. So here we go, our first example, solving a direct variation problem. The area of a rectangle varies directly as its length. If the area is 50 square meters when the length is 10 meters, find the area when the length is 25 meters. All right, so what we want to do first, step 1, is set up our model. It says since the area varies directly as the length, we can say that A equals K times L here. So we've got direct variation involved. And again, it didn't have to be X and Y with K. I mean, they're using variables that make sense here since we're talking about area and length. A varies directly as the length. So that makes sense. And then 2, it says since the area is 50 when the length is 10, we can easily get K by substituting in down here. Say 50 equals 10 times K, and in our model here. Divide both sides by 10, and we get that constant number is 5, which we are going to take and stick back into this model. So if A was equal to K times L, using this information in this first part of the sentence, this 50 and this 10 gave us this number 5 here, and now we can relate that to all problems involving the rectangle. So to find the area when the length is 25 and answer the question, step 4, we're going to plug that 25 back in and say 5 times 25 is 125. So the area of the rectangle is 125 square meters when the length is 25 meters. What do you think? Now, we can do some more here. If that one didn't quite hit you, let's try a few more. You know me, I don't do one example and say, that's it, see you next time. Young does many here to try to make sure you understand the concept. So direct variation is an nth power. Let n be a positive real number. Then y varies directly as the nth power of x or y is directly proportional to the nth power of x. So see, they can also make up models where you have y equals k times x to some power n here. So direct variation is that way, and notice we can do it inversely as well. Inverse variation is the nth power. Y would equal k over x to the n power here. So y varies inversely as x, as we talked about earlier. Let's get to some problems with it, though, so we can learn how to set things up. Now, let's take a word problem here. Usually word problem students are scared. But see, if you can set up the model and go through these aren't too bad. So this one reads, in a certain manufacturing process, the cost of producing a single item varies inversely as the square of the number of items produced. If 100 items are produced, each costs $2. And then it says find the cost of the item if 400 items are produced. So what we're going to do first, it says let x be the number of items produced and y be the cost per each item. Then for some non-zero constant k, y would equal k over x squared. Y varies inversely as the square of x. Step 2, it says then substitute. Since we know that we've got 100, y equals 2 and x equals 100, we can go ahead and solve this. Now, of course, 100 squared would be a 1 with 1, 2, 3, 4 zeros would be 10,000. And multiplying through by the LCD here of 10,000, we can get k is 20,000 in this one. We're going to take that 20,000, plug it back in the model, so the relationship between x and y is as read here. So now we can answer the question. So when 400 items are produced, the cost per item is 20,000 divided by 400 squared, which would be 0.125 if you did it on your calculator. That's nice, you can use those. Now, in money terms, of course, that would be 12.5 cents. So these inverse and direct variation problems are used a lot in real life. Now let's look at one where there's a combination of things. Let m and n be real numbers. And again, we can pick any variables we want here. Then y varies jointly with the nth power of x and the nth power of z if there exists such a non-real number k. So here is a one that's got a whole bunch. Now this looks like it's all directly related. Y equals k, x to the n, z to the m power. Now do you see why there's no inverse variation in this one? Because if you don't use the word inversely anywhere, there's no division here. So this is a joint problem that involves just direct variation. And it says note that and in the expression y varies jointly as x and z translates as the product. The word and does not indicate addition here. So again, things to watch out for. I mean, if they were wanting to use some kind of direct variation involving addition, they would make it more clear. So let's look at one here. It says the area of a triangle varies jointly as the lengths of the base and the height. Now, we know this from the formula for the area of a triangle. So it says a triangle with base 10 feet and height 4 feet has an area of 20 square feet. Find the area of the triangle with base 3 feet and height 8 feet. All right, so can you set up the model here? Think about that. And here's what we're going to come up with. Let A represent the area, B the base, and H the height of the triangle. So here is our model. A equals K BH. Notice it varies jointly as B and H here. Not any mention of the word inversely, so no division. Since A is 20 when B is 10 and H is 4, as promised, they will give you enough information to get K. Plugging in K is a half. Now, once you know K, plug that back into the model, step 3 to get the new model. So there is our formula for the area of a rectangle. I wonder where they came up with this stuff. A equals 1/2 base times height. They probably did this enough time and kept coming up with this model, and they said, wow, this is always going to work. It's amazing. So step 4, when B is 3 and H is 8, plugging in, we can answer the question. So 1/2 times 3 times 8, which would be 24. Half of 24 would give us 12 square feet. And let's just do one more example, because you know Young gives you plenty here. Let's do one that's got a whole bunch of goodies in it. I think after this one, it should bring it home. So example 4 here says, the number of vibrations per second, the pitch of a steel guitar string varies directly as the square root of the tension and inversely as the length of the string, for you guitarists out there. See, so you didn't know that math was involved in your music, but math is involved in music. So if the number of vibrations per second is 5, when the tension is 225 kilograms and the length is 0.6 meters, find the number of vibrations per second when the tension is 196 kilograms and the length is 0.65. So we've got some direct variation here, and notice we've got some inverse variation here. All right, so let's see if we can set up the model on this one. So we're going to let N represent the number of vibrations per second, and you can pick other letters if you want. T represents the tension, so that kind of makes sense here. And we'll let L represent the length of the string. So from the information we just went over from there, we can say that N varies directly as the square root of T and inversely as L. So here is your model. Now notice K is always when you have an inverse variation problem in the numerator. So make a note of that. K is always in the numerator here if it's inverse. All right, and the rest is just kind of like it's read, isn't it? All right, now we did get enough information here. Substitute the given values for N, T, and L to find K. So they gave us these values. They said N was 5. The tension on the string when it was starting out was 225. The length 0.6, because the string on guitars is kind of, you know, thin there. And we can solve here. We'll get the square root of 225 equals 3 there. Now what they did is they multiplied through by the LCD. Now we can get rid of that 0 on the 0.6, so we can just do that. So these will go chop chop out, and 0.6 times 5 will give you the 3 there. Now the square root of 25 is a nice square root. It's 15, so 15K equals 3. Divide both sides by 15. And K is 1/5, which in this case we might want to change to 0.2 just to make it a little bit easier when we plug it back in our model. So substitute for K, and we get the new model is N equals 0.2 times the square root of T over L, the tension and length and so forth. And then, of course, we can answer the question. Now use the second set of values to find T and L to get the N there. So plugging in, we will get 0.2 times the square root of 196 divided by 0.65, if you do it on your calculator, should be approximately 4.3. So the number of vibrations per second is approximately 4.3. And this concludes our section on direct, inverse variation, and combinations of the two. So go ahead and slam that homework and let's bring home some A's. Bob Young signing off.